This is your friendly neighborhood physics teacher here, and we're going to talk about forces that are at an equilibrium. And yes, there's going to be vectors involved. So equilibrium uses vector components of forces. Basically, it uses your breakdown into your x and y component. As I said in the free body diagram video, we have to break it just like how we do projectiles. When we had to do a triangle at the beginning, you have to do that for forces as well. There we go. So we have a gentleman that's pushing a lawnmower. If you think about it, if you've ever had to mow a lawn, especially a push lawnmower, you are actually pushing it at an angle. So you're pushing it down, and in this case, it'd be to, so we're looking at it, it'd be to the right. Now, our equations can't handle things at angles. Just like in projectiles, we could only handle things that were true horizontal or true vertical. It's the exact same thing with forces. We have to break it down into its x and y components. So the y component is down, and the x component is to our right. And you would have to either do a, sine, cosine, or tangent, or a Pythagorean theorem to figure out those different components. Same thing with this. You're pulling a little red wagon, your force is going up, and in this case, to the left. So we would have to break down into its x and y components to figure out how much of that force in the angle is going in the horizontal, how much of that force in the angle is going in the vertical. We have to do it. Yes, you do. You have to do it. Our equations, F equals ma, cannot handle that force at an angle. We have to break it down into its x and y components. Now, if you notice, the more, pretty much the lower the angle gets, the less that's going in the vertical, which kind of helps in the long run because you're not picking up the wagon, you're dragging it to the left. So the more that's going in the left direction is more efficient. So again, SOHCAHTOA is playing a main part in this. You don't have to memorize them. It is on your formula chart. They just don't use O and H. They use A, B, C on your formula chart. So let's do this one together. So we have a force at an angle. So when we have a force at an angle, again, we have to break it down into its x and y components. So this is our y force and a y, and this would be our force in the x. And this would, and then the green one would just be our force. So let's do our force in the x first. So we're doing force in the x first. Oh, before we do that, we need to figure out what is our sides of our triangle again. So this is a 90-degree angle here. This would be our hypotenuse because it's at the angle. If our angle is here, this becomes our opposite because it's the opposite side of the angle. And this becomes our adjacent because it's next to the angle. It's adjacent to the angle. So if we were going to do our f of x first, we would end up having to use our cosine. Because cosine theta equals adjacent over hypotenuse. So cosine and our theta is 39 equals our adjacent, which is our f of x, times our hypotenuse, which in this case is 250. We were trying to get our f of x by itself, because that's what we're looking for. This is being divided. The opposite divide is multiply. And what you do to one side, oops, you have to do the other. There you go. Come on. Why all of a sudden can I not write? There we go, multiply. That cancels out. And we're left with 250 times cosine angle is 39. Now, if you're in pre-cal right now, there's a few things you got to watch out for. Pre-cal deals with in radians. Physics deals with degrees. So you have to make sure your calculator's in degrees. Your phones are automatically in degrees. Apple phone, Android phones are automatically in degrees. If you're using a graphing calculator, you have to put it in degrees. If you reset it, it naturally goes into radians. I'm not very sure with Desmos, so definitely look up that. If you're using Desmos, definitely look that up and pay attention. But we have to be in degrees. Now, if I'm with an Android phone, you can just plug that straight in. 250 cosine 39, and it'll give you the right answer. Apple phones are a little bit backwards. You have to plug the 39 cosine. You have to put 39, hit the cosine button, and then times it by 250. So Apple's work a little backwards. So let's check it out. So we have our so pretty much going to show all of the work I just did. I wanted to kind of walk y'all through it a little bit before just clicked along. So that's your adjacent, that's your opposite. So again, you end up getting that your y is sine theta. I think I put x before. I am so sorry. You get that, and then your cosine. Your cosine is your x. And again, multiply both sides by 250, and you get 194. Now I did round these, so we didn't have to necessarily deal with decimals because we're just practicing. And yes, you have to do this every time you see a force at an angle. You have to. Have to. But luckily enough, in most cases, your x is going to be cosine and your y is going to be sine. But always double check your hypotenuse, opposite, and adjacent to make sure. So in this case, again, exact same setup, it's just going down instead of up. So we have to draw our x and y components, or a y and our x, since that's the way we drew it. That is a 90-degree angle. So this is our force y. This is our force in the x. And our green is just our normal, our force. If we're looking at, there we go. If we are looking at this angle. This is our hypotenuse because it's at an angle. This side would be our opposite because it's opposite of the angle, and this side is our adjacent. So again, our Fy would be our sine. And I went ahead and skipped kind of moving things around. You just automatically get your 75 sine of 25. And you get a negative 34. It being negative makes sense because it's going down. For your f of x, you use cosine, you get 67. Again, it's positive because it's going to the right. So 34 of the 75 pounds is going down. 65 of the 75 is going to the right. So the majority of it is going to the right. Now, this is where things change a little bit. When I said most of the time, sine is your x is sine, your y, your x is cosine, and your y is sine. This is the one case that it changes. So now, your force, your red, which was your force of y, is now the one that's parallel to the motion. Because if you had an object here, it's rolling down. And your F is now perpendicular to the motion. So you have a ball that's rolling down the hill. Your force of gravity still stays straight up and down. But to make things easier, we're going to rotate our frame of reference. So normally, our frame of reference is like this. Come on, please write. X is horizontal, Y is vertical. We're going to rotate it slightly. We're going to rotate it so our X goes with the motion. So now this is our X, and this is our Y. So the red force, I didn't mean to do that. Just love it when things stop working. Love of technology. There we go. So this is now our force in the X, and that is now our force in the Y. And our 90-degree angle is there. Kind of cool. So if the guy was trying to figure out how much he had to counteract from keeping the big boulder to run down the hill, you would have to figure out your force of X. But your weight or your force of gravity would still be 75. That does not change. Now, this, if you put your scale at an angle, you would actually tell that your weight on the scale would change because it would only be checking your force in the Y. Cool thing about geometry, the angle, that's the question mark, and that 27, guess what? It's the same. Now, I cannot remember what law of geometry this is. What I want y'all to do is, my in-person people, go ask Mr. Lambert what law this is. He's the teacher next door, and he can tell you what law this is, but some law of geometry. So getting a little bit more into equilibrium. So equilibrium is the addition of all the forces is 0. So the sum of all the forces is 0. That little E, funky, fancy looking E, is called a summation. And so sum means add. Or you can just put net force. The reason it's called a net force is because it's all the forces in one direction that are affecting it. So think about when you throw out a net and you're catching all the fish, you're throwing out a net and catching all the forces. So this girl's hanging there and is at equilibrium. So if we have her weight, or her force of gravity, which is 60 pounds, going down, it's negative because it's going down, how much is each arm, yes, you heard me right, each arm balancing out? Because she's at equilibrium, she's not moving, she's not swinging, she's not doing anything, she's just hanging there. So if 60 is going down, how much does each arm have force on it? Hopefully you said 30 pounds each, because 30 plus 30 gives you 60. And if you have 60 going up and 60 going down, you're at equilibrium, because you have negative 60 plus 30 gives you 0. Now, let's say she magically grows a third arm. How much does each arm have now? Hopefully you said 20. Because think about it. If she was holding by one arm, and you sit there and hung by one arm, you're having your whole weight with that one arm. That's why it's easier to hold if you have two arms up. And then obviously it's going to be even easier if you had three arms, because each arm is getting less and less weight put on it, or force put on it. So again, at balance, because negative 60 plus 20 plus 20 plus 20 equals 0. That's why knowing the direction matters with force. That's why force is a vector. Because if we just did 60 plus 20 plus 20 plus 20, that's not going to get us 0. That downward force of 60 matters, so it needs to be negative. Okay, in this situation, we have a table. The table weighs about 20 pounds, and then we have a 90-pound anvil on the back end of the table. So this leg is getting a force of 50. This leg is getting a force of 30. The other leg is getting a force of 20. So how would we figure out how much the front leg's getting? So again, it's at equilibrium. The table's not moving. So that's saying all the forces going down, which would be our 90 and our 20, have to equal all the forces going up, which would be the four legs. So you do negative 90, minus 20, because they're both going down, plus 30, plus 50, plus 20, because those are all forces are going up, because that's the force of the ground on the leg. So those are basically normal forces. And you just solve to get the missing force, because your net force, or your sum of your forces, is 0. So let's do a little bit of math real quick, shall we? Not what I meant to do. What is that? There we go. So let's figure out what this is. So if we have 8, so that is 80. So 80 plus 20 gives us 100. So all the known, so this, and this all give us 100. And then 90 and 20 give us 110. So that means this sucker has to be 10 pounds, because that's what we're missing. So a negative 110 plus 100 gives us 10. So we're 10 off. Well, it gives us a negative 10. So there's still negative 10. There's 10 more going down. So we need to balance that out. We need 10 on this leg. So it's just a balancing, just trying to make it equal to 0. So another thing is think about. So we have a 1 kilogram mass. So we learned that on Earth, if we have a 1 kilogram mass, it equals 9.8. I'm rounding it to 10 just to make quick math. So if we put 2, and this is a spring force, because this is a spring scale that we're measuring with. It's like if you step on a scale to get your weight, it's a spring scale. Let's say we put 2 spring scales on it. What would it end up reading? Hopefully you said 5 each. Because if it's 1, 10, 10, put 2, half of 10 is 5. Now this is what confuses a lot of people. It throws a lot of people off. Now with those two, and we've stretched them to kind of go at an angle. And as you can see, these spring scales are reading like 15. So why would they be reading more? The reason is again, you have to draw in your x and y components. Your y components are still 5. Because 5 going up, those add together, still get the 10 that's going down. So your 5 going up plus your 5 going up cancel out your 10 going down. But since it's at an angle, that force has to be greater. So that force ends up being 15. So hanging things at an angle is not always the best. So your net force in the x direction is 0 because this balances this, and your net force in the y is 0 because these two balance the one going down. So if you have a weight going down, this kind of shows you, so when you have one that's counteracting straight up, it's going to be that same weight. But as you expand it out, as you angle it out, your forces are actually have to get bigger and bigger and bigger. So the more you angle the string, like if you're hanging something at an angle, the more you angle it, the greater that force on that string is. So honestly, if you plan on hanging something, it's better to hang it straight up and down than it is at a weird angle. For example, weird angle. So we have a box that's 100 pounds and 2 strings that are 30 degrees is holding it. We want to know what that's called tension force. We want to know what that tension force is. It's tension force because it has a string. So going up, if you have 2 strings going up, so what would that yellow force be? That yellow force should be 50. Again, we have 2 strings, so therefore we have 1 string that's handling 50 going up, the other string that's handling 50 going up. We're only dealing with 1 string now, so we just take half of the force. So if it's 100 going down, half of that would be 50 going up. There you go. Kind of visualize it. 100 going down, 2 50s going up. Now, this is a 30, 60, 90 triangle. Again, there's a lovely little geometry rule there that you can figure out. So you actually do end up being 100 pounds because of that lovely rule. You can also sit there and figure it out. So here, dealing with your sine. So this sign is a little weird. You never want what you're looking for on the bottom. You never, ever, 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 ever want what you're looking for on the bottom. So what you're going to have to do is you're going to multiply both sides by your question mark here. That cancels out. So you get question mark. Sine sine of 30 equals your 50, and then again, you just divide your sine of 30. That cancels out, and you're left with question mark equals 50 divided by sine of 30. And you plug that in your calculator, you should get 100. Again, it needs to be in degrees. Calculus once in radians, we're not, or pre-cal once in radians, we're not in pre-cal, we're in physics, we deal with degrees. It needs to be in degrees. So, and of course, since it's a mimic, the other side is 100 also. So as your angle changes, what did I say? Your tension increases. So if you do sine 10, your tension ends up being 280. The lessens even more, ends up being even more. And of course, it's like 1 degree ends up being even more. Okay. So it's your requirement to keep this lovely, crazy building clean. That's including dusting the really crazy light fixture hanging from the ceiling. So you need to pull the light fixture to the balcony so you can actually dust it. How much force do you need to pull that light fixture? There's your little dust. So we know that the light fixture is 650 pounds. The light fixture's not moving, so it's at equilibrium. So that means it's not moving at all. So after you sit there and drag it towards you, then it's not moving. So I will say it's moving while you're dragging the thing to you. But the net force in the X and the net force in the Y is 0. It's at equilibrium now that you have it, you're dusting it. So that means your upward force is still going to be 650. We're trying to figure out what force we need to pull it at so we can get it to us. And we can safely dust it. And for some reason you have amazing eyes and you can eyeball that it's at about an angle of a 32. So since we know, so if we remember, this is hypotenuse, this is our angle, this is our opposite, this is our adjacent. So we can use tangent, which is opposite over adjacent. We're trying to get our question mark by itself, so we're going to multiply 650 by both sides, and we get that we have to pull it at 410 pounds of force. That's a lot of force to get that heavy thing to us so we can dust. Now, let's just for giggles, let's figure out what our tension is. That's our hypotenuse. So we can actually use cosine. I personally would probably end up using sine just because that's what I'm normally use, but we're trying to give you different ways. So I used cosine. We never want what you're looking for on the bottom. So you would have to manipulate that tension. Multiply both sides by t. And you get that your tension times, cosine of 32 equals your 650. And then you can go ahead and divide your cosine 32. So you would get your T equals your cosine. Oh, running out of way. Running out of room. Let's try it again, shall we? You would get your T equals your cosine, or divided by your 650 divided by cosine of 32. You plug in your calculator, and you would get your tension equaling 770 pounds. So you're adding extra force by tilt. So when your light fixture was hanging straight up and down, that tension would have been 650. As you bring it to you to dust, you're actually adding more force to that light fixture. You're adding more force to that string, or that tension force to the light fixture. So you really hope and pray that moving it doesn't affect it. Now, all of those, so far, either A, you only had to deal with one piece of string for tension, or 2, both tensions were the same. What about a situation when both tensions are not the same? So like this hammock here. You can see that the hammock isn't quite tilting the same way. Our right side's a whole lot taller than our left. So now we have 2 tensions to deal with. The hammock's not moving. So we know that our net force in the X and our net force in the Y are 0. It's at equilibrium. We just need to figure how much tension our right side's having, how much our tension our left side's having. So we have to draw 2 triangles. The hard part here is we don't know. Before, we knew exactly how much force was going up because they were equal. You just take how much force is going down and divide it. We don't know that. We don't know that. We do not know that information. So if we just look at our forces in the X direction, again, remember that this is the hypotenuse. Our angle's here, so this is the opposite. This is our adjacent. Again, hypotenuse, opposite, adjacent. So what we did, looking at the X direction, we did on this side cosine of theta equals adjacent over hypotenuse, and we just kind of plugged in things that were going on. So our cosine theta, which was 9, equals our adjacent, which is our force in the X, divided by our hypotenuse, which is our force of tension 1. And then we just got force of tension 1 on the other side. So that went up there. And we did the exact same thing over here. Cosine theta is adjacent over hypotenuse. Our theta is 21. Our adjacent is our force in the X. And our hypotenuse is tension 2. Running out of room. Tension 2 times tension 2 causes that to cancel. You just get that your force X on this side is equal to that. And since they're going in opposite directions, the one with the angle at 9 is going to the left, so it's negative, and that equals 0. So that's the forces in the x direction. Now we have to do our forces in the y direction. Again, our other times we've known what it was. We don't know what it is now because it's not balanced. So we would have to do opposites. We would have to do sine. So sine theta is opposite over hypotenuse. Sine theta equals opposite, which is our force in the y, divided by T1. Again, we want force of y, by itself. That cancels out, so our force of y is T1 sine theta. And we do this side. Again, sine theta is your opposite over hypotenuse. Sine theta, we know the theta on this one. Theta is 9. Our theta on this side is 21. Our opposite is our force of y. Our hypotenuse in this case is force T. Cancel, so our force of y equals our tension force sine 21. That's both going up, so it's going those two plus the negative 180 that a gentleman weighs would balance each out and equal 0. It purely becomes an algebra problem now. It does. It purely becomes an algebra problem now. We are going to take the top problem and solve for our tension 2. We're going to take the top problem and solve for our tension 2 because we don't like dealing with that negative. Let me erase this real quick. I really don't like negatives because I tend to drop them if I don't pay attention, especially if I'm trying to go fast. So if I could get rid of the negative, I'm going to get rid of the negative. So since it's a negative on this side, I want it on the other side because I'm trying to get the T1 by itself. So I'm going to add T1 cosine of 9 to both sides. Again, at this point in time, I'm just trying to get this by itself. So that cancels out. So therefore we have T2 cosine of 21 equals T1 cosine of 9. We want T2 by itself, so just divide both sides by cosine. So we get that our T2 is just our T1 cosine of 9 divided by cosine of 21, because we're just getting our T2 by itself. And we're substituting. We're plugging all of this into that. And now we only have one unknown. Before we had two unknowns. We didn't know what T1 or T2 was. But now we only have one unknown. We can mathematically solve for our T1 now. What happened here is sine over cosine, our cosine times sine equals tangent. I pulled out the T1, and then you just divide over sine of 9 plus cosine 9 times tangent of 21, and divide that by 180, and you get your 360. Once you get your T1, take it to your problem over here, plug it in, and you can solve for your T2. So there are going to be some problems you have to do algebra. This is an algebra-based physics course. This is just substituting. That's all it is, substituting. So let's look at this problem. So again, we have a box. It's being hung at two different angles. So we have tangent 1 and tangent 2. So again, our forces in the x are equal, but our forces in the y are definitely not going to be equal with the triangles because we have 2 arrows going down versus the 1 arrow going up. And you do the exact same situation. Now these two are the more complicated versions. You might see one problem like this on the test. It would be a free response problem. And yes, you need to show every single step. You need to show every single step. So hopefully you understand sine, cosine, and tangent. You understand that velocity components are pretty much the same thing as force components. Vectors type of thing. And that you understand what equilibrium means. You do have a practice thing with equilibrium. Please go give it a try. I'm also going to link a Khan Academy that would help also. Remember, you're loved and appreciated. Have an awesome day. Bye.